In this video, we're going to look at how we use what we know about kinetics to figure out potential reaction mechanisms and talk about what that means for a reaction moving forward. So just what we are going to do for reaction mechanisms will look different from what you will do when you get to organic chemistry and do reaction mechanisms, but what they are is the same. So when we talk about reaction mechanisms, we're talking about a series of individual steps by which the overall reaction occurs. So I'm going to start with an example and a mechanism that goes with it, potentially. That's what we're going to propose. So for an overall reaction, we're going to look at H2 gas plus 2ICl gas turning into 2HCl plus I2. And we have a proposed mechanism and in the proposed mechanism, step one is that H2 reacts with one molecule of ICl and it turns into HCl and HI. And then in step two, HI reacts with the other molecule of ICl and it makes another HCl and I2. All right, so a couple of things. First, now that we have talked about the collision model, you can imagine how these molecules would have to line up in order for this reaction to take place. All right. Now the other thing is that in my two steps, I have this molecule that doesn't appear in my overall reaction. So let's see what happens. These are individual steps that tell me how the overall reaction occurs. So let's add these reactions together, right? So nothing new. We have added reactions together before. And if you add these reactions together, step one plus step two gives you the overall reaction, and those HI molecules cancel out. So this cancels out, but it's a necessary part of the mechanism. So HI is something that we call a reaction intermediate. So a reaction intermediate is a species that forms in one elementary step and is consumed in a later step. have a little reminder before we go into the next section. So remember this from way back long ago when we first started kinetics. You cannot determine the rate law from the full balanced reaction. Cannot, absolutely cannot. You have to determine the rate law experimentally. However, when we are dealing with elementary steps, you can use the equation for an elementary step to get the rate law for that step. So for elementary steps, which are like the steps in this mechanism, you can use the equation to find a rate law for that step. All right, so this means that we do need to set up some, if the step looks like this is what the rate law would look like. And my hope is that this is something that makes sense. I'm sorry that it's something true for elementary steps that's not true for full reactions, but it is a key part of what lets us figure out if a mechanism would make sense for a reaction when we put it together. So for an elementary step, we're going to write what the rate law would look like. And then I'm going to give you a name for something called the molecularity, which is just a fancy name to describe how many things are reacting with each other in this step. So if my elementary step looks like A going into products, meaning this one molecule just kind of falls apart or rearranges itself or something like that. The rate law here is that rate equals K times the concentration of A. So A is the only reactant that appears, and so it appears with its coefficient as the exponent in the rate law. And this would be a unimolecular step. So only one molecule is participating in this step. All right, so hopefully the next example we'll start to build this up and it'll start to make a little more sense. So if A reacts with another molecule of A and turns into products, the rate law here is the rate constant, and then I have A. If I followed my pattern, I'd have concentration of A times concentration of A. Well, that's concentration of A squared. And this time there are two molecules reacting. So we call this a bimolecular step, right? Because it's just one of the steps in the mechanism. It's not the full balanced reaction. So also bimolecular, right? I just did one with two molecules of A. Well, what if I have two different molecules reacting, right? A plus B turning into products. My rate law is K concentration of A times the concentration of B. Still bimolecular because I have two things reacting. They just happen to be different things. And this is about it for elementary steps. We can put another one on here because they bring it up in the book, although it's a really bad idea to propose something like this because it happens essentially never. But if you had A, and A reacting, or A and B, or A, B, and C, right, three things reacting in this one step. Right, well, I have A three times, so I have A cubed. This is a termolecular step. And this is incredibly rare. So here's the thing. I listed in the table, but you will not, or you should not, see a mechanism that has a term molecular step in it. And then just as a reminder, these words are how we characterize the elementary steps. And I promise that this is actually going to help us with reaction mechanisms. So in a reaction mechanism, so just like if you think about the steps that it takes you to get through any task at all, some of the steps are slow and some of the steps are fast. So if you think about, let's say your task is waking up in the morning and getting out of the house. There are a series of things that you have to do in order to do this, right? You have to wake up and get out of bed. You have to get dressed. You maybe have to eat breakfast, take care of other people or animals. And so one of those steps will take longer than all of the others and will be the determining factor in how long it takes you to get out of the house. So for me, that's probably actually getting out of bed in the morning, right? So like the amount of time that I spend sitting and looking at my phone and trying to avoid starting the actual day will be the deciding factor in how long it takes me to get out of the house. Now, for a different person, that deciding factor might be not packing lunch the night before, and so you spend more time packing lunch than doing anything else, and that is the determining factor in when you get out of the door in the morning. So in our reaction mechanisms, we have steps that do this, and so some are slow, some are fast, and every single one of them has a rate determining step. So much so that we do abbreviate this as the RDS. And so this is the elementary step in a mechanism that is so much slower than the other steps. So this rate determining step is so slow that first, it limits the overall rate of reaction. And it limits that rate so much, it determines the overall rate law for the reaction. So let's take one example reaction to look at this. So our example is going to be the reaction NO2 gas plus CO, turning into NO gas and CO2. So the mechanism for this reaction is that in step 1, NO2 gas plus NO2 gas turns into NO3 gas and NO. So this might look a little weird, right? We have only one NO2 in our main reaction, but if you had even a tiny number of moles of NO2, that's a lot of molecules of NO2. So we have a lot of molecules around. Two of them could interact with each other. And then in step 2, the NO3 reacts with CO, turning into NO2 and CO2. All right. So I'm going to label these with whether they are slow or fast. And this is how you will see them labeled in problems in your textbook or in any of the problems that I give you where you have to deal with mechanisms. What it will just say next to it is slow or fast. And it might have parentheses around it or something like that. So this is how it will be labeled. So what this is telling us is that step 1 determines the overall rate law because it is slow. So there can only be one slow step in your mechanism. So being slow means it's the rate determining step. That also means that you can use it to write the rate law. So based on this step, put a little star by it, and we will write the rate law from it. So NO2 plus NO2, this looks like that bimolecular step where A and A reacted with each other. So my rate law based on this mechanism is that the rate is going to be the rate constant times the concentration of NO2 squared. Now it's not really the final thing because you still have to know, and in this case I'm just going to tell you, that it's consistent with experimental data. So what I will ask you to do with mechanisms is a couple of very specific things. Before I give you that whole list, actually, I want to stop and do this as an energy diagram. So this mechanism has 2 steps. Let's see what the energy diagram would look like. So it's still energy on my y-axis. It's still a reaction coordinate on my x-axis. So 2 steps, it just means that I have 2 bumps in my energy diagram. So my first step, there's some barrier to getting the NO2 and NO2 to react with each other, and then there's some barrier to getting the NO3 and the CO to react with each other. So my energy diagram might look something like this. So these are my reactants, my products. I've got an energy barrier for each step. And then this extra low spot here, these are the energies of my intermediates. So in this case, it's the NO3, but this sort of extra well in here, that's not a reactant, it's not a product, that's the extra stuff that you're making in your mechanism that then cancels out in the overall reaction. So on my reaction coordinate, right from here to the intermediates is step 1. And from the intermediates to the products is my step 2. So if you look at which represents step 1, which represents step 2, the thing that you can see about the rate determining step is that it has the tallest hill on the entire diagram. And so this is the other way that you can figure out which one is the rate determining step. It has the highest overall energy. So if the second step were the rate determining step, the second hill would be higher than the first one. And we're going to deal with those types of situations in a little bit. All right, so what are you going to do with mechanisms? So you can't prove a mechanism, not even in organic chemistry, although there are some, generally accepted ones, and some will be better than others. So what we are going to do, I'm not going to ask you to propose them. So let's make sure you have that down. You can't prove a mechanism. And I won't ask you to propose them. I'm not saying that someone later won't. You can show that a mechanism is valid. So everything that I have told you about mechanisms, you can put that together and say, this is a mechanism that someone has given me. Is it valid for the reaction that it goes with? So in order to be valid, there are 2 criteria that you have to meet, which means there are 2 things that you have to show me in your work. And the first is that the elementary steps add up to the overall reaction. Which means you have to show me this or indicate somehow that you checked this when you're telling me whether or not it's valid. And if it doesn't add up here, don't even bother with the next step, because the mechanism can't be valid if the elementary steps don't add up to the overall. If they do, the next thing that you need to check is that the rate law predicted by the mechanism is consistent with experimental data. And you must show that both conditions are met. So let's see what this looks like. So the question will say, is the proposed mechanism valid? Or show that the proposed mechanism is valid. So in this case, it says, is the proposed mechanism valid? For the reaction is 2NO2 gas plus Cl2 gas turning into 2NO2Cl. And is it valid if the experimental rate law that the rate equals K NO2 squared, and the proposed mechanism is that in step 1, NO2 gas plus Cl2 gas turn into ClNO2 and Cl. This step is slow. And in step 2, another NO2 gas plus Cl gas turn into ClNO2. And this step is fast. So, is the proposed mechanism valid? We have the equation, we have the experimental rate law, and then we have these two steps. So the first thing is to check if the steps add up. So when I add these two reactions together, I get 2NO2 plus Cl2 plus Cl, and then I get 2ClNO2 plus Cl. Those Cl's cancel, and yep, this matches. So yes, the reactions add up. And then I check the rate determining step rate law. And so I will go to this step and I will just write the rate law based on that elementary step and then check it against the experimental. So this is rate equals K times NO2 times Cl2. Oh, that does not match. My experimental rate law is that it is second order in NO2, and then the rate law from the rate determining step says that it's first order in NO2 and first order in Cl2. This is not a match. No match. So the conclusion is that the mechanism is not valid, and that's it. We don't have to try to fix it. We don't have to try to come up with a new one. We can just say that based on the criteria, this is not a valid mechanism for this reaction. If they had matched, then we would just say, yes, this mechanism is valid. All right. So what if the slow step is not the first step? So let's stick with the two-step mechanism for right now, and we'll see examples of where this gets a little bit longer. But what if the first step is fast? So in the first step, your reactants turn into intermediates. And they do this very quickly. And then the second step is where we get the traffic jam. So whatever happens in the second step, it's slow. So you can imagine that in a scenario like this, the first step, it's just making intermediates, go, 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 go. And then you just have all of these intermediates hanging around because the second step is going so slowly that they just kind of sit there waiting to react. So when this happens, the intermediates build up. So much so that they turn back into reactants. And you've seen something like this before. Hopefully, assuming we're still talking about kinetics after this other chapter. The result here is an equilibrium because that forward reaction is still happening, but now the backward reaction is starting to happen. And this means we have to deal with an equilibrium, and it also affects the rate law. So you cannot have intermediates in a rate law. So if you write a rate law based on the slow step and it contains intermediates, you must find a substitute. Now, thankfully, this is what the equilibrium will allow us to do, but it is an extra set of steps that you will have to take to indicate whether a mechanism is valid for something that has a later step that's slow. So let's do this as an example. So our question is the proposed mechanism valid? And my reaction is 2H2 gas plus 2NO gas turning into 2H2O gas plus N2. And the experimental rate law is the rate equals K, concentration of H2, concentration of NO squared. The proposed mechanism that I have has 3 steps. In the first step, 2NO is in equilibrium with N2O2. And this step is fast. And I'm going to start labeling the equilibrium constants the rate constants for each of these. And it's just to keep track of which step they came from. So the rate constant for step 1 will be K1. And then for step 2, we'll have K2. For step 3, K3. In this case with the equilibrium, right, K1 is for the forward reaction, so we'll sometimes do K minus 1 for the reverse reaction, and that's just a subscript label. So it is the rate constant for going backward, and if you remember, one of our equilibrium definitions was that the rate of the forward reaction equals the rate of the reverse reaction. Okay, step 2 is H2 gas reacting with N2O2. This is the second step, so I'm going to call my rate constant K2. It turns into H2O and N2O. This step is slow, right? So this is my rate determining step. And then step 3, N2O reacts with H2. This gets a K3 because it's step 3 to make N2 gas plus H2O gas, and this is a fast step. So the question is it valid? The first thing we have to do is what we do always, is add up the steps and see if what we get matches the overall reaction. So what do we have? 2NO plus 2H2 plus N2O less N2O2. And it makes N2O2 plus 2H2O plus N2 plus N2O. My N2O2 cancels, my N2O cancels, and 2H2, 2NO, 2H2O, and N2. That looks perfect. So yes, the reactions add up. So far so good. We're happy with this. So then you go to the rate determining step to write the rate law. So step 2, we're going to use this to write the rate law. And when you do so, rate equals K2, H2, N2O2. Yikes. So first, it's not a match. So you get maybe a little disappointed because we haven't had a good match yet. But it has an intermediate. So you must find a substitute for the intermediate before declaring it's not valid. So it's still possible that this is not a valid mechanism, but having an intermediate in your rate law doesn't allow you to say that. So we need to substitute it to get the intermediate out and then go back and compare it to the experimental rate law. So I did bring up earlier the definition of equilibrium, and we will find the substitute for this intermediate in the equilibrium step. So the definition of equilibrium is that the rate forward equals the rate in reverse or backwards, however you want to say it. So because these are elementary steps, that means my rate laws are equal for these two. And let's just write these down, and hopefully you'll be able to see where we can make some substitutions. So from step 1, the rate law for the forward reaction, which we can still do. It's not the rate determining step, but it's still an elementary step in the mechanism. So this is a valid thing to do, is K1 times NO squared. And the rate of the reverse reaction is K minus 1 times the concentration of N2O2. So these are equal to each other. So we will set them equal to each other. And you get K1 times NO squared equals K minus 1 times concentration of N2O2. So in the rate law that I wrote for my rate determining step, the thing that we need a substitute for is the N2O2. So if I can solve this for N2O2, I have something that I can algebraically substitute into my rate law. So let's do that. All I have to do is divide by the K minus 1. So concentration of N2O2 equals K1 divided by K minus 1 times the concentration of NO squared. And now this can be substituted in to that rate law that I wrote from step 2 of my proposed mechanism. So if I do this, rate equals K2 times the concentration of H2. And then instead of N2O2, I'm going to sub this whole thing in. K1 over K minus 1 times NO squared. Now, it feels wrong, and I don't know why it feels wrong, but remember, these are constants, right? K1, K minus 1, K2, they're all just numbers. So leaving them separately is like leaving a 5 and a 10 divided by 2, right? They're just numbers. They have units on them. We don't have to deal with the units in this part. So let's collect them all together. And then we're also, right, if we collect them all together, K1 times K2 divided by K minus 1. Now it's like I've just written my 5 times 10 divided by 5. We're just going to abbreviate it as K. It is a rate constant that came from multiplying and dividing other rate constants together. So my rate law from the mechanism now is H2 NO squared. And this matches. So this is great. This is a match. So we have now met the second condition. So yes, this mechanism is valid.